This is a continuation of our video on energy and systems. So we just finished the roller coaster problem, and I just want to, before we do another example, I want to say a word or two. First, remember that if you have non-conservative forces internal to the system, mechanical energy, you can't say it's conserved. You can't. Okay, in the problem we just did, the coaster and Earth system, the roller coaster and the Earth, the internal force between them was gravity, and that is conservative, so we were okay. I mentioned the normal force. Of course, the track itself is not in this system, so that's an external thing, and it was applying a force to the coaster. So I said that we were still going to say it was isolated, but I would just want to talk about that for a second now and make sure we're okay with that. Normal force is kind of special. It's technically a conservative force. I won't get into the details of that. But see, of course, the normal force is going to be, or almost always, perpendicular to the motion, right? Because it's pointing upward and the object will be moving along the surface. So it'll be perpendicular to the motion, so it doesn't do any work, right? The work would be zero. And so it can't add or subtract energy anyway. So even though it's an external force, it's not adding energy or taking energy away. So we can still treat the system as if it were isolated from an energy standpoint anyway. Okay, so that's what we did in that last problem. There was an external force, the normal force, but it just wasn't involved in the energy game at all. So from an energy, when we're doing the energy approach, it's like it's not there. So we were justified in still using conservation of mechanical energy. Okay. Let's try a new problem. 2-kilogram block is pushed against a spring, compressing it 20 centimeters. The block is then released, projecting it along a frictionless surface and then up a frictionless incline at 45 degrees. So how far up the incline does it travel? Okay. So we have a situation that looks like this. We have a spring. We have an object attached. And then it's going to go up an incline, which is at 45 degrees. Okay, so this guy gets pushed in. So here's the 0 point. So this guy's already been pushed in 20 centimeters. And then we're going to let it go. So the spring's going to push it until here, and then the block will go on its own. It's not attached, it's just pushed up against the spring. So the spring will push it back to here, and then it'll slide along, and then it'll go up until it runs out of steam. And that's the question, is how far up the incline does it travel? So how far up does it go? We'll call that D. All right, so we're going to use the energy approach. It would be possible to do an F equals ma kind of approach where we work out forces. Actually, it'd be tough because the spring is not a constant force, so actually we're not really equipped to do it. It's possible, but we haven't really gotten into that with the spring force. Okay, but the energy approach is going to be pretty simple. The spring and block and earth system is the system we want to look at, because the only external force then will be the normal force of the surface and the inclined surface as well. But remember, that external force doesn't participate in energy transfers, so we can ignore it, or it means the system really can still be treated as isolated. And the internal forces, well, there's between the spring and the block, so there's a spring force, and between the block and the earth, there's gravity, and those are both conservative. So Normal force doesn't count, so it's isolated, and we only have internal forces that are conservative, so we get to use conservation of mechanical energy. So we get to say that the mechanical energy it has right way back here at the beginning is going to be the same throughout the whole trip, and in particular it's going to be the same as it has right at the end. So we can say that the initial sorry, hold on. My pen went a little crazy there. The initial kinetic energy plus the initial potential energy equals the final. And we can just do that right from the initial point to the final point, just in one jump in the energy approach. Okay, so at the very beginning, right when we release it, it just for that first moment has no speed, right? The spring's going to start pushing it, but at the very beginning it's at rest. We're just letting it go. We're not giving it a push. So it has an initial speed of 0, and so that means it has no kinetic energy. But it does have potential energy because of the spring, right? The spring has been compressed, and that's why the spring now is going to start pushing it and turning that potential energy into kinetic energy. But that hasn't happened yet. Right at the beginning, it's all potential energy. And we know that the formula is 1/2 kx squared for the spring potential energy. All right, and now it's going to travel, it's going to go all the way up, and then when it's up here, the very top, it'll come to a stop. Of course, then afterward, it'll probably start sliding back down because it's frictionless. But at the very top, it will have no speed, so again, it'll have no final kinetic energy. But it will have potential energy, this time because of gravity, because it has been elevated. So that'll be mgy. That's the formula for gravitational potential energy. Now, we have to be careful here. Y is literally the elevation, not the distance it traveled. So we'll have to translate y into d, doing a little triangle thing at the very end. Okay, but that'll just be some quick math at the end. So what we can do then is solve this. We have 1/2 kxi squared equals mgy. I guess I'll call it yf because it's the final y. Yeah, okay. So easy to solve, right? I get yf, and I'm just going to divide by the mg. So I get 1/2 kxi squared divided by mg is my yf. That's so easy. All right, so yf is, and I just put in my numbers. I got 1/2. I've got spring constant of 500 newtons per meter. 20 centimeters is my initial x. I need that in meters. 2 kilograms for my mass. And as always, 9.80 meters per second squared for acceleration due to gravity, giving me 0.51 meters. Yeah, so easy. Like that's. I hope you can appreciate. I'm not going to. Well, I said we can't really do it because I haven't taught you the details of the spring force when it comes to F equals ma. But hopefully you can get, like, that would have been a much bigger involved problem to try to work out the changing force while the spring pushes, to figure out the acceleration that whole time, to try to figure out how fast it's going at this point. Then this part is fine because it's just going to go at a constant speed, but then we'd have to do a whole F equals ma on an incline here with gravity and the normal force, and and we'd have to work that out and do some constant acceleration equation here. Whereas here is just, okay, here's how much energy it started with, so that's how much energy it ends with, so this is what the y has to be. Very, very direct and pretty easy. Okay, as I said, we have this little, we have to deal with a little triangle, a little right triangle here, because the question actually asks for the hypotenuse, like how far up it went. We have the height. So just to finish this off, we can just say that what do we have? We have that YF is going to be d times the sine of 45 degrees. Yeah. So d is YF divided by the sine of 45 degrees, which is 0.72 meters. So that's the actual answer. That's how far up it went. 72 centimeters, I guess, since our other number was given to us in centimeters, we can give our answer in centimeters. Okay. So that's a good problem and really showing off the power of the energy approach. Here's another problem. We have another block, 1.60 kilograms, and we're going to drop it from 2 meters above a spring. So in other words, the spring is like vertical. And maybe it's got a little platform or something. And the block is up here. So we're going to drop the block downward, and it's going to land on the spring, and then the spring is going to compress, right? Because the object's going to land on it. And the question is, how far down does the spring compress? Okay, so I'm going to put a coordinate system, a vertical coordinate system on it, call it y, and I can make 0 be anywhere I want, and I guess it probably doesn't really matter too much. I'll make 0 be where the spring is before it gets compressed, so the at-rest position of the spring. All right, so if our system consists of the block and the spring and the earth, then we can say that this is isolated. There would be a little bit of air resistance. The air would be an external force, but let's ignore that. Let's assume there's not too much of that. And the internal forces are going to be the spring force and gravity, right? Those are internal because we're including both the spring and the earth in our system. So we have conservative internal forces. And so therefore, we get to say that mechanical energy is conserved, so that the total mechanical energy at this point is going to equal the total mechanical energy in the after position, which will look like, here's my y-axis, 0 is here, and the block has pushed the spring down a bit. And that's what we want to know, right? We want to know how far it got compressed. Okay, so the mechanical energy in this picture equals the mechanical energy in this picture. All right, so Ki plus Ui equals Kf plus Uf. This is another example where, okay, it's the kinetic energy at the beginning. If the block is just dropped, that would be 0. And the kinetic energy at the end, when the thing has gone as compressed as it's going to be, and it kind of comes to a stop, at least temporarily, the kinetic energy at the end will be 0. Kinetic energy is not always 0 at the beginning and the end. I just happen to be doing 2 problems in a row where that's the case. Okay, now potential energy. Well, in the beginning, we've got all potential energy, right? So gravitational potential energy, because the object is up in the air, mg times its initial y, which is 2 meters. And then the final potential energy. Now this is actually interesting because we definitely have spring potential energy. We have 1/2 k xf squared. But by the way, because this is a vertical spring, x is really y. So 1/2 k yf squared. But also, there's a change in altitude, so there's gravitational potential energy as well. And actually, we went below the 0 mark. We went below sea level, so to speak. We kind of have a negative altitude here. So we actually have to include that as well, plus mgyf. And yf is going to end up being negative, right? We see that. This is the positive side, this is the negative side, and that final y value is going to be below 0. But we have to account for that too. That's potential energy that matters. So we're looking for YF. Okay, so yeah, we have 1/2 k YF squared plus mg YF. Now, algebraically, this is interesting because we're looking for YF. We have everything else that I haven't underlined. But just from an algebra standpoint, that's a quadratic. And, you know, these are slightly more annoying to solve. Let me put in all the numbers at this point because I'm not really going to just solve for YF here. I'll show you what we're going to do. Let me put in the numbers. So I've got m and g and the initial y over here, and that turns this guy into 31.36. And in fact, I'm not even going to write units just for a second, just because I want to show you something. 1/2 k gives me 4.25 times 10 to the third, and again YF squared. And then mg right here will be 15.68 YF. Okay, so just with the numbers, that's the equation that we now have to solve. If what we usually do, if you remember your algebra from high school with quadratics, you put everything on one side. So I'm subtracting minus 31.36 over to the other side, and that just leaves 0 on this side, which I'm rewriting now. And you can use, at this point, you can use the quadratic formula to solve that. Or probably your calculator, most calculators, most good TI graphing calculators also just have an algebra solve command, which I encourage you to solve, because your calculators, if you do that, your calculator is just going to put it into the quadratic formula anyway. So no need for you to remember or look up the quadratic formula and type it in yourself. Just have your calculator solve it for you. So solve on calculator, or go to wolframalpha.com. However you want to solve this, have it numerically work out the answer, and we will get. So my calculator is actually giving me negative 0.0878 and also positive 0.0841. Now we know quadratics typically often give you two answers, so we picked the one that's physically possible, and we were expecting a negative answer here, and so that would be this one. So YF, the final Y, is negative, and let me just change it to centimeters, let's say negative 8.78 centimeters. So the spring will compress by 8.78 centimeters when that block hits it and pushes all the way down. Okay, at this point, I'm going to give you a problem for you to try. And here it is. So a 4 kilogram block is let go from rest at a height of 3.60 meters, and it's just going to slide down a curved ramp. It's frictionless. Sorry, I didn't write that, but it's frictionless. And then it's going to slide all the way over, and then it's going to hit a spring here. So this is similar to the ones we were just talking about. Two questions. How fast is it going at the bottom of the ramp before it hits the spring? So how fast is it going in this stretch right here? And then when it does hit the spring, how far in does it go? How far does the spring compress? And so this is one I'd like you to try and just write on a piece of paper and bring that to class on Wednesday if you would. Okay. All right. I'm going to stop this video and pick up in another part and just do one or two more examples.